Hi, everyone. I'm Marie Diener-West. I'm a professor in the Department of Biostatistics at the Johns Hopkins Bloomberg School of Public Health. I'm happy to be with you today to talk about an introduction to logistic regression. So this should hopefully be a gentle introduction to logistic regression. We'll start with a motivating example. We'll look at relating a 2x2 table to measures of association as well as logistic regression. And then we'll look at motivating us a simple logistic regression model using Stata, as well as the interpretation, the appropriate interpretation of the output from Stata for this logistic regression. And we'll end with other considerations and an overall summary. So our motivating example is to set up logistic regression to make statistical inference regarding the prevalence or incidence of binary events. A binary event is one that has only two possible outcomes. So for example, our outcome of interest Y may take on only two values, supposedly 1 or 0, and 1 would indicate the occurrence of the event, and 0 would be the non-occurrence of the event. The example that we'll be using is a community trial of almost 26,000 preschool children in 450 Indonesian villages in Banda Aceh. The children were randomized to either receive vitamin A supplementation or a placebo, meaning no vitamin A, and they were followed for the binary outcome of death by 12 months. So the questions that we may have are, what are the best estimates of the true death rates, the proportion who die, in the vitamin A group, which we'll call P1, and the placebo group, which we'll call P2. We'll also be interested in asking, is there statistical evidence that vitamin A reduces childhood mortality? And if so, how strong is the evidence that vitamin A reduces childhood mortality? So before looking at the example data, let's review 2x2 tables and common measures of association for 2x2 tables. So we have here on the left-hand side a 2x2 table in which the rows are the group 1 and group 2. The columns show us the number of events or no events. And then we also see the totals for each group in the column on the right. The totals for event, no event are in the row on the bottom. And of interest to us is the question, is there an association between group and event? Another way of asking that is there a dependence between having an event and what group an individual is in? So the measures of association that we use to try to answer this question are the risk difference. So on the right-hand side, we see the risk difference is just the difference in the proportion who have the event between group 1 and group 2. We use the symbol P1 hat to indicate that this is an estimate based on the data from the table, but it's estimating the overall truth in the underlying population. So P1 hat is the proportion who have the event in group 1 minus P2 hat, the proportion who have the event in group 2. So that difference in risk or difference in proportions using the data in the table suggests that A over A plus B is the proportion who have the event in group 1. We're subtracting C divided by C plus D, which is the proportion having the event in group 2. So if there is no association between group and event, this risk difference would be equal to 0 or near 0. Another measure of association instead of the difference is to look at the ratio of the proportion with the event in group 1 divided by that in group 2. So that is known as the risk ratio, and we would see the numerator is the proportion having the event in group 1, A over A plus B. The denominator is the proportion having the event in group 2, C over C plus D. But then there's a third measure of association referred to as the odds ratio, which is used in logistic regression. Let's first define what odds are. Odds are P over Q. In other words, the probability that the event Y equals 1 divided by the probability that the event Y equals 0. And if we look at our notation in the table, we would say the odds of the event in group 1 is the proportion with the event divided by the proportion without the event. So that's A over A plus B divided by B over A plus B. So that's our overall numerator. In group 2, the proportion having the event is C over C plus D. The proportion without the event is D over C plus D. So here is the odds in group 1 divided by the odds in group 2, which we know as the odds ratio. So let's look at the math we can perform. So we can cancel out the denominators. We're left with A divided by B in the numerator. In the denominator, we cancel out, again, the denominator of C plus D. We're left with C divided by D in the denominator. And after a little bit of mathematical rearrangement, we see that that is A times D over B times C. This is a common shortcut that's given in many epidemiology textbooks, for example, but it really depends on the table being set up correctly. So I always advocate looking at the odds ratio in terms of the odds of the event in one group divided by the odds of the event in the second group. So now that we've defined those measures of association, we can look at this slide, which reminds us that we have 3 different measures, but the risk ratio is one that is used for prospective study designs, in which we start out with the exposure, for example, and then look at the outcome of disease, whereas the odds ratio is commonly used for both cross-sectional study designs as well as case control studies. And just a reminder of, how do we interpret this odds ratio? So if we defined the odds as being P over Q, which we do, but if we used a common example of P, the probability of rain on a certain day is 0.75, then Q is 1 minus 0.75, that should say, which is 0.25. And the odds of rain would be 0.75 divided by 0.25, which is 3 divided by 1, which is 3. So we would say the odds of raining are 3 to 1 on a particular day. And if we had 2 days that we were comparing, we could have an odds ratio. So let's go back to the motivating example where we have the community trial of children who are randomized to either vitamin A or placebo and followed for 12 months for the binary outcome of death. So this is a prospective study design, and we'll be asking the question of what are the best estimates of the true death rates or true death proportions in both the vitamin A and non-vitamin A groups. What are the best estimates of the true risk difference and risk ratio? And is there statistical evidence that vitamin A reduces childhood mortality? So here are the data from this trial. We can see that the group is given in the first column. We can also see that the total of 23,682 is listed in the bottom of the second column, and that the totals that were randomized in each group were 12,094 in the vitamin A, of which 46 were seen to have died by 12 months. So the proportion who died, or the death rate, is 0.0038, and that's what we'll call P1 hat. In the placebo group, which we'll call group 2, there were 11,588 children. 74 had died by 12 months. So the risk of death was 0.00639, which we call P2 hat, or the risk of death, the proportion who died in the placebo group. So our risk difference is the difference P1 hat minus P2 hat, which is a negative 0.0026. So that would suggest that if we multiply by 100, that there's a 0.26% lower risk of death in vitamin A as compared to placebo. The risk ratio is taking 0.0038 divided by 0.00639 to give us a ratio of 0.6. So remember, if there's no association, the risk ratio would equal 1. This is suggesting that the risk in vitamin A is 0.6 times that of the risk in placebo, or in other words, there's a 40% reduction in the risk of death in the vitamin A group compared to the placebo group. So we could perform a chi-squared test of no association. So here, our null hypothesis is no association between death and vitamin A exposure. The alternative hypothesis is that there is an association between death and vitamin A exposure. We can see that in STATA, we're using a cohort study immediate command. So CSI stands for cohort study immediate. And we're inputting the actual totals of 46 deaths. This would be in the vitamin A group. And in the, and that's considered the exposed group. The unexposed group is the placebo group, in which there were 74 deaths out of the total. So we see here the risk in each group is what we had obtained by hand on the previous slide. So we've annotated here that P1 hat is 0.0038, P2 hat is 0.0064. So this is the risk in the vitamin A, this is the risk in the placebo. And then we can look down and actually see that we have the risk ratio as 0.596, or approximately 0.6, what we had calculated by hand. But we have a 95% confidence interval here for the true risk ratio, which ranges between 0.41 and 0.86. It does not overlap 1. So if we think of the null hypothesis, no association between death and vitamin A would be the same as a null hypothesis that the risk ratio equals 1. Since this confidence interval does not overlap 1, we would reject the null hypothesis. We see here the chi-squared statistic gives us a p-value of 0.0051, much less than the value of 0.05, our typical significance level. So based on this p-value, we would also reject the null hypothesis. And our conclusion would be based on the data, there appears to be an association between death and vitamin A with a lower risk of death in the vitamin A group compared to that in the placebo group. So that was for a prospective study. As I mentioned, logistic regression is used for either a case control or a cross-sectional study. So we're going to turn our attention to an example of a case control study that's using the data from the Banda Aceh prospective study. So we created a case control study by taking the 120 observed deaths or cases from the prospective study. Then we matched children who were alive based on age and gender to those cases. So that gave us a case control study in which we have 120 deaths and 120 who were alive. And we looked back then out of those 120 who were matched on age and gender to see if they had received vitamin A, and 61 had, and 59 had not. 59 had received placebo. So now let's consider this as a case control study where we have dead and alive, and we looked back to see whether they received vitamin A or placebo. So now we have a new 2x2 table. There's an overall total of 240. 107 received vitamin A, 133 placebo. And we can now calculate the odds of receiving vitamin A among those who had died. So again, we'll use the data to look at the proportion who had vitamin A among the deaths. That was 46 divided by 120. So that's our P1 hat. We'll divide it by the proportion who did not receive vitamin A among those who died, 74 divided by 120. And we cancel out the 120s. We would see that the odds of vitamin A among those who died is 46 divided by 74. Then we would look at the odds of vitamin A among those who survived. And the proportion who had vitamin A is 61 out of 120. The proportion who had placebo is 59 divided by 120. The 120s cancel out, and we're left with 61 divided by 59. So this allows us to see an odds ratio, which is equal to the odds of receiving vitamin A among those who died, divided by the odds of receiving vitamin A among those who remained alive. And we take 46 divided by 74, divided by 61, divided by 59, and we get 0.60. Now, this happens to be the same odds ratio that we saw in the prospective study. And part of this has to deal with the fact that we have very rare events. Death is a very rare event. But now let's look at how we could perform a chi-squared test of no association in a case control study. So in Stata, there is a command called the CCI, case control immediate, where we put in the cell counts for the inner 4 cells of the 2x2 table. And we can see here that we have out of the 120 deaths, we have out of the 120, we have 46 that were, out of the 120 who were dead, there were 46 who had vitamin A. Out of the 120 who were alive, there were 61. We can see the odds ratio is given here at 0.6, and we see a confidence interval, though, for the odds ratio that is wide and overlaps the value of 1. So again, if our null hypothesis is no association, then the null hypothesis is that the value of the odds ratio equals 1. So based on this confidence interval, we would fail to reject the null hypothesis, conclude that there appears to be no association between vitamin A and the event of death based on this case control study. And we also can look at the chi-squared statistic here. This is giving us a p-value that's a little bit bigger than 0.05. So based on our significance level of 0.05, we would fail to reject the null hypothesis and conclude there appears to be no association between death and vitamin A receipt.
With this, we come to an end of the part 1 of this session, which was on the introduction to logistic regression by Professor Marie Diener-West from the Department of Biostatistics at Johns Hopkins Bloomberg School of Public Health. This presentation is a part of the first part of the series with 2 parts explaining simple logistic regression, and also includes a session on multiple logistic regression and a demonstration on Stata version 16. We hope you enjoyed this session. Thanks for stopping by.